I would be continuing my previous class here. We would be talking about dewatering. In the previous class, we studied on the principles of dewatering, why we should do the dewatering. Essentially, this is because you need to remove the water and then make it possible for construction to proceed in the for foundations. Essentially, for dewatering, we should be able to understand the hydrogeology of the area, as I just mentioned. The aquifers we have, in fact, we studied this in our undergraduate curriculum, in which you have two types of aquifers. One is a confined aquifer, the other one is unconfined aquifer. You also have perched water table, where the water tables exist in some localized areas, and so one should be able to understand the hydrogeology of the area and also the permeability, because this is an important parameter for design, and also what are the design issues, like how much of water should be excavated, removed, so that that area is a little free of water and you can go ahead with the excavation, and also see that the excavations are stable. So, in the process of excavation, one should make sure that the water is removed and also it is stable. So, these issues we should address, and just I would like to take a few minutes to recap what we did, what we understood. We need this for essentially for construction of excavations, and when you are trying to go for structures below the water table. And sometimes the permanent dewatering systems are very expensive. Normally we go for temporary excavation systems, and we also try to have some measures to release the hydrostatic pressures generated. We have varieties of equipment that we use. We need to have sumps, pumps, trenches, well points, deep wells and all that, and this is a typical example in which one can lower the groundwater table, like this is initial water table, and then by having this sort of pump and arrangement and a ditch and all that, one can lower the groundwater table. This is another one which we call it as well point system, in which again there is a water table here. Because of this well point here, we are trying to lower the water table from here to here, and this is the bottom of the excavation. So, at least about 1 or 2 feet below the water should below the foundation level, the water should be drained off. This is a typical system in which you have headers and all that, and this is an example that I just discussed. This shows you the applicability of the different types of groundwater dewatering systems. Depending on the grain set distribution characteristics, one can have these systems, like say for example, if you have a very fine material, you will have electroosmosis, which we will discuss in a short while. And also if you have the grain set distribution in say for example 0.01 to 0.06 or 0.07 range, one can go for gravity drainage, like you just go to the lowest point and start withdrawing water. So, by gravity and by the other force, it will water will collect at one point, and then one can remove the water. So, this is an important thing, because one should understand which what type of soils are suitable for drainage and what type of drainage one can have. So, for example, in clays you cannot have a gravity drainage. There is some sort of applications in which you try to really reduce the seepage pressures beneath the foundations, like sometimes extensive instrumentation is also placed, like piezometers we have. What happens is that if this is an excavation, the possibility is that if this is the initial water level, there is a water pressure that comes in this fashion, and if you are able to release that water pressure in some sense, like putting the water pressure to nearby aquifers and also have a release system here, then it is fine. This is a typical field situation that we come across, that we should always design, say for example, if an underground structure, you may have to design for some sort of uplift pressures here that are generated. In fact, this results in a very expensive designs, in the sense that the thickness of the raft or whatever foundations that you are going to have would be very thick compared to the other loading conditions. So, we should so this is some of the typical cases that we have seen, and this is a typical groundwater lowering scheme next to the building. Suppose you have a see, the thing is that if you try to dewater a lot, there is a possibility that there is a definite settlement, because groundwater lowering results in increase in effective stress, and what happens is that if the increase in effective stress is that there is a settlement that takes place. So, sometimes before you try to have a system wherein you try to withdraw the water, at the same time try to pump back the water in such a way that you do not have a appreciable difference of the effective stresses between this foundation and this foundation. So, it is not easy. So, you have a well point system here, but again you have a recharge point here also. So, you must be able to design your system in proper way such that you are able to lower the groundwater table, but also recharge next to this foundation. So, for example, you are having a recharge point next to this, close to this foundation, though this two well points are trying to remove the water from this area, there is one pump that is one point wherein you are trying to pump in lot of water, such that the effective stress between these two foundations is not very different, and then so that it does not lead to lot of settlements. Sometimes this is the way that we calculate the different settlements that we are already we know about this, and sometimes we use cutoff walls and trenches to prevent the damage. For example, you can have you are trying to have a dewatering system here, deep well here, and then you have removed the water level from top level to, say for example, from here to from this point, and it is always better to have some sort of cutoff trenches also, because the cutoff trenches or cutoff grout curtains we call them, they are a little more impermeable compared to this soil. The soil or an aquifer is essentially a sandy system in which the permeability is going to be high. The moment you make this well point system, there is a tendency for the water to rush back and then see that the groundwater comes back to the original condition, but we do not want that. What we try to do is that this area is free of water, but at the same time we would like to intersect this flow line by putting this sort of a curtain, which is something made of impermeable materials, like it can be even bentonite, it can be geomembrane, it can be a cement slurry and all that. This is another interesting system in which say for example, one can lower the groundwater table next to the slope. So, there is a well here, and then you also can have a sand drain here, such that this is also connected to the aquifer here. So, what happens is that once it is connected to the aquifer, the possibility is that all the water goes down here and the pore pressures are not mobilized very so the pore pressure is somewhat released, it is taken to atmosphere. So, that is what it means, that it is serving as a protective system. Actually, in this context I must give an example that there is one area where I was just trying to understand one case study, wherein there was a particular bus stand area where there is lot of water logging in that particular place, and then people wanted to within the before a minister visits that area, they wanted to keep that area completely dry. And we normally in in Indian context we use all low lying areas for certain bus stands or certain important locations, but then you always see that always a water logging is a problem. So, what the solution there was that the field engineer was wise enough, he wanted to dewater the whole area, but he did a survey of what is the hydrogeology of the area. When he looked at it, he saw that there was a permeable stratum like this, it's a sandy layer exists about say 10 meters down. So, what he did was that, imagine that this is all a area that is close to a bus stand or something like that, but then there was a water logging because of the presence of water table close to the groundwater table, close to the ground surface. So, what he did was exactly that, he just took made it a hole like this, put some geosynthetic drains, prefabricated vertical drains, and connected them to the sand drains, sandy layer that existed here, with the result that with a proper spacing and all that, he was able to connect the whole the area which was waterlogged to the sandy layer that existed below, and maybe within one or two days the whole area that was supposed to be waterlogged, it totally drained off. So, it was an interesting example that I must mention, that effective understanding of the hydrogeology of the area coupled with proper understanding of the problem helps in giving us good solution which is cost effective. So, when you are trying to design a system like groundwater dewatering system, you must be able to know what is the height of the groundwater table above the excavations. For example, you have at the bottom of the excavation minus 10 meters, and if the water table is minus 5 meters, you must be able to dewater 5 meters. And then if you want to dewater, only the permeability of the ground is the important parameter, and we saw that number of methods are there to find out the field permeability. In fact, one must only use a field permeability test, because the laboratory tests are quite could be misleading, because you may not take samples properly and all that. So, one should do pumping system tests or even packer tests to find out the field permeability and use that in the design. In fact, this is one single well approximation, in which if you want to know the discharge, and if you know the height of up to the impermeable layer, then this is the H naught is the height. And so, you have this sort of expressions which we studied in undergrad courses in irrigation engineering and other subjects, where you know how to make the discharge calculations. If you have wells, this is a standard problem in which you will have this particular this is the phreatic line after pumping, and so this is a phreatic line before pumping. So, because of the withdrawal of water, it comes down to this level, and so these are all the various variables involved, and you can get the discharge. And then that also, like if you are able to have two wells successively, one can use level difference between in the two wells to measure the permeability as well. This we discussed, and there are certain expressions here. Say for example, in the previous case, this Hs is known as the height of free discharge surface, and there has some relationship H minus H naught divided by H into C. Like essentially there is a sort of a little above, there is a water degree of there is a water layer exists, not exactly close to the phreatic line that we see, like not exactly like this, but there is a HS layer at which it can be wet, and this is an important factor. And to find out the influence range, like the length at which the area over which one can the dewatering system is going to be effective, one should have the understanding of what is the length of the area or the area of the aerial extent. So, there are some expressions available in literature which are little empirical, but then there is no other way here. So, there are some empirical relationship given in this expression, which is related to the height and also the permeability of the soil and also the free height. So, this is the expression that I was just mentioning as I just ended at this point, where if you have one well point, one can calculate permeability. So, we have a number of wells 1, 2, 3 or n, it could be n, and you have a calculation of the discharge. One can use this x1, x2, xn are the distances of the wells, and L is the influence area. So, one can think of a circular arrangement of the wells, and the expression is in this form, like where A is the area the radial distance of the well points. So, this is an important expression, and one can, how do you really now, suppose there is an apartment area which is trying to come up in the dried lake bed, but still there is always a possibility of what table exists there. You would like to construct apartments, and you would like to go for basement flooring, and there is some sort of construction that you need to take up. So, how do you get all these parameters? We will see. How do you get the spacing is something that we should get the total quantity of water to be pumped. So, for example, this is the equation that I have given. So, this suppose imagine that this is a circular area, and then this is a discharge that you have from so many number of pumps. There are some 5 pumps, 8 pumps here. So, if they are all radially distributed with a radius A, you will have a discharge from this expression like this. This is all given in standard textbooks, particularly Hausman and other books one can see. So, what we do is that we should be able to get the optimal estimate or some estimate of the total quantity of the water to be pumped, the values of height of that this thing, and y is another variable, and r are the r or L actually to be determined by the type of aquifer, the required drawdown and the soil type. If A is the radius of the equivalent circular area and x and are the dimensions of the excavation, you get square root of, say for example 10 meters by 20 meters, so square root of that divided by pi. So, this gives the circular the diameter or the radius of the equivalent circle, and so we know that you can get the total quantity, and you know you can also have the expression for single well. So, knowing that you just get the number of wells. So, this is what we do. We will just give some example also on that. In fact, so once you know you have different types of pumps also, like you know for example in India Kirloskar, there are so many companies, one can have a lot of information from this pumps industry, and depending on the diameter and they have different, these pumps have different capacities, discharge capacities as well as the heads they can handle. So, you can see that a 3-inch pipe is sufficient to handle, I mean it can handle heads up to 90 meters, and then it can give a discharge in terms of so many gallons per minute. So, this sort of relation one should understand, you know actually the company will give you this sort of information, and many of the companies they will have their own information. So, I mean they have their own a lot of experience connected with this, and this is another type of expression, same thing of course higher ones, like the what I showed you was a lower pump, lower size. This is 3 inches, 4 inches, 6 inches and 18 inches pump size. You can see the discharge capacity is very high, like even 1500, 1800 gallons per minute, and then the head is also like for the same head. So, one can really have a good, one should the choice of pumps is also an important parameter here, and of course, this is another example of the bottom of how do you avoid the bottom of the heave. You know in fact, what happens if you just do the groundwater lowering, the possibility is that the water gets you know there is an uplift here, and so we try to really release the pressure to this point. Say for example, you can see that this is a blue line, you can see that. So, you need to see that this condition is like the total stress at a particular point is more than the water pressure plus, this is actually the unit weight of water into the height plus the z, you know the depth of this thing. So, one should take care of these conditions. I just want to give a small example here. And you have a building to be constructed on the ground which has the following ground conditions. Dimensions of the building about 30 to 20 meters is plan area, like you can say this is 30 meters, this is 20 meters, and the depth of excavation is 10 meters. You have to go down 10 meters, and the water table is at ground level. So, and then the permeability of sand deposits below the ground level is about 10 power of minus 3 meter per second, and this is an average value, and the depth of water level has to be decreased by about 2 meters below the excavation level. So, in order to construct the building, dewatering has to be done by laying pumps at various junctions. Calculate the rate of flow of water when one pump is laid and compare it with a discharge when a number of pumps is increased. So, this is like we would try to solve this problem. You have a 30 length is about 30 meters, width is this, and depth is about depth of water table lowering required is 12 meters. And what do we do is that first thing is that we should calculate. So, we note down all the conditions required, and the permeability values 10 to the power minus 3 meter per second is that value. Drawdown, depth of drawdown below the level is 2 meters, and this is H is 12 meters. In most cases there is an empirical relationship to obtain the approximate value for the line of influence, as I said, equal to R. This is given by this previous expression that I just mentioned, and you have some sort of expressions like this that are given in the text, and once you use that for C equal to 3000, you get a term called about 190 meters or 200 meters close to that, and the formula for discharge is given by this equation, and if you put all these numbers you get about 0.0433 meter cube per second. So, this is actually the discharge that the area has, totally this amount of water that should be thrown out to see that you have that water table is does not affect the construction of the foundation at 10 meters level, because 10 meters level is coming into picture, and then we are trying to take at least 2 meters down that. Just this is an example, maybe numbers and field applications could be different. I mean, so but then just want to give a flavor of what could be done here. I am just trying to illustrate. And expression for a single yield from a single well is given by an expression which is actually an empirical expression that is given in Hausmann. And so you try to have the for substituting r equal to 0.1 meter, the radius of the single well, and h naught equal to 2 meters and k equal to -3, the yield for a single well is obtained as 0.01 meter cube per second. Hence, like we have seen that the total water to be removed is 0.0433 meter cube per second, and this is from 0.01. So, you can take it as about 4.3 or something you will get, but you can say for the safe side, I mean conservative side, 5 wells are required. 5 wells or 5 well points are required to calculate to dewater the area. This is an example here. Now, see what are the distances we should calculate, right. So, if the number of pumps are increased to more than 1, it is not easy to have a high you should have one pump of very high capacity, which is not easy sometimes. In fact, sometimes what happens is that in most of the field applications, if one of the pumps goes wrong, there should be a factor of others should take care. So, they always have some efficiency factor that comes into picture here. So, one should be very careful. So, this particular equation gives discharge for a number of wells, like if you have number of wells, it is x1 and then the distances x1, x2, x3, xn, and take natural logarithm and 1 by n is the number of pumps, and use this. In this example, we say that as I just mentioned, we need 5 pumps. So, and then we try to put at different locations, maybe just like this x1, x2, x3, some example. This is only an example here. So, you try to put this and then calculate the numbers here, and what you get is 0.058, which is more than 0.0433, right. So, which is not bad, which is okay, like it is better to have a higher little margin here, so that there is always that if there is something goes wrong, you always have some safety. So, hence x1 with all these distances, of course, many of these are just numbers, one can change the numbers and then get these things. What this means is that one can get design the number of pumps required based on the discharge required or the boundary conditions that we have for the given problem, and also have adequate margin of safety. So, this is a simple example illustrates that one can do a design of the dewatering system in a simple way. And of course, in this particular issue, one should understand that the use of the dewatering techniques needs considerable experience. For example, it is not easy, you have specialized contractors who will have array of their systems. If one goes wrong, they can use something else. Particularly if dewatering goes wrong, it is very risky in foundations, and a lot of problems will come up all of a sudden. So, one should understand that these techniques need lot of experience, and many of the terms and parameters in the formulas have uncertainties in the variable, and then you need to trial actually. What I meant was that you should be able to do some sort of trials in actual design. Say for example, you must try to do a simple trial in the field itself. Is that I got a permeability like this, and then I got the water leveling system. They need to measure also. In fact, they must measure the using piezometers and all that. What is the extent of lowering the observed? They have to do a lot of some measurements, so that it is quite useful in trying to see that the design is satisfactory. Finally, if it is not going to work in the field, it is very difficult to retrieve the situation, particularly if the water table problem is not solved. It's the project gets stopped. So, that is very important thing. One should understand that many of the variables formula are somewhat empirical, and they are highly variable also, like say for example, permeability value. There could be variations from point to point. So, even if you take average value also, one should be little careful, and one should design the system in a proper way. So, with this I have just completed dewatering, and we have another system. How, see, the thing is, I just mentioned that dewatering, particularly when it is in clays, how do you do that? The thing is that this is a very important, and we use this concept, because we know that the clays are negatively charged particles, and we try to use this concepts to dewater in the case of clays. So, that is called electrokinetic stabilization, that we will discuss. So, in this lecture, what I would be doing is that I would be completing or covering a few issues on electrokinetic processes and describe a few field trials of the technique. One of the most important causes of the foundation movement is the volume change of the active clays. For example, the bentonite clay, or even say for example expansive clay, or any general clay, soft soil has lot of issues, particularly in the presence of environment, like for example, if there is a water content changes, there is a lot of swelling, water content is there, it imbibes water, there is a water content change, and there is a swell. So, many of these clays have a lot of difficulties, particularly they have shrinkage and volume expansion and all that, and the electrokinetic stabilization is a technique of applying an electrical current through the soil mass to promote the migration of chemicals from injection points. What we do is that the chemicals will we introduce also some chemicals, so that we also have some injection wells, and once you apply the electrical gradient, like electrical gradient, you have a cathode and an anode, there is a movement of anions, and then that draws water with that. So, when the movement takes place, because of the preferred orientation or the migration of ions, whether it is cations or anions, then water is also moved in that process, and with the result that you have stabilization occurring. Actually, it is very useful to weak clay soils that require sundering and yet possess a low hydraulic gradient conductivity. So, the permeability is very low. So, for example, if I want to do a consolidation in consolidation process, it takes lot of time, even preloading and all that, they work to some extent, preloading, or even the technique of what you call we discussed vertical drains also. In fact, you may not believe, vertical drains have been combined with this technique to accelerate the process further. It is not just people have advanced so much that in the initial stages we had only sand drains, now you have the prefabricated vertical drains, you also have natural drains. Now, PVDs have electrical system, you make some of the drains as electrodes, and then you see the rate of water movement. Like I have seen myself some actual experiments where the migration of water is so fast, like the moment you have an electrode, there is an anode, there is a cathode here, and then you apply some 3 or 4 millivolts in a small tub, then the water, within a few hours. Say for example, I did an experiment once upon a time where you have a plastic tub in which the water content of the whole area was about 18%, and then it is a compacted soil, and you have a cathode, you have an anode, and then we have applied some sort of electricity between that, and then when the water content was 18% in both sides, after maybe another 4-5 hours or 6 hours, the whole in one side there is a 3% only, the other case it was little higher, much higher, but then one can see that to reduce the water content to such from 18% to say for example 5% or whatever, it needs enormous stress in the field, like pre-consolidation or the load that you have to apply is so much, but here, and then time is also another important variable, and without going for loading or anything, you are able to just by electrical forces, electrical gradients, you are able to withdraw all the water from one side, one electrode to other electrode just by voltage difference, because the it was compatible. In fact, this was required. Why? Because there was one software company, and then they have constructed, they have a flooring and everything. They did not see that there is a water table level that existed about within 4-5 meters down there, very close to that and whatever. So, the flooring that they have was not really comfortable, in the sense that it is all wet, and then there is a water, somehow it went capillary, because of the capillary rise of water. Water even was you can see that the flooring totally, it was it has lot of waviness in that, and it was very uncomfortable. In a very good software office, it is actually DEC in some time back, maybe a few years back. So, in that whole software office, when people go, it is supposed to be a people that is a excellent environment where people work very comfortably, but what we saw was that finally people are not able to use it well, because you have waviness, there is a water in some corners, and you have all computer systems here. So, when they approached the Indians of Science, I just did that experiment and looked at the possibility, because already the building is existing and I can't use all these systems of dewatering and all, not easy. So, we studied this electrokinetic stabilization as in one of the courses, and we did an experiment to see that. That is what I just mentioned, that we just took a plastic tub in which we introduced electrodes, and then we try to find out the water content change after applying the electrical gradient. So, we find that it was excellent, and only thing it was required, it needed a lot of practical experience in installation of that particular system, but because it is not easy. So, as I just mentioned, this technique is very useful to very weak clay soils, and which has lot of I mean low permeability, and so sometimes people also use chemical grouts also. Okay. So, some of these things could be avoided if you have to go, if you can go for this type of technique. So, what does it do? When an electrical potential difference is applied to a soil across a soil mass, cations and anions are attracted to the cathode and anode respectively, whereas neutral particles are attracted to neither. That is actually there is a standard reference by Gray and Mitchell, and this forced migration occurs most readily by the ions with the greatest mobility. So, for example, you have different types of ions like sodium ions, potassium ions and calcium ions and all that in clays. What happens is that the ions with the greatest ability, like say for example sodium, they can it is a very comfortable system in which you can they have a good mobility, and then migration of water. Essentially we are looking at removal of water occurs rather fast. Within the soil mass, these ions are to be found in the pore water existing between the soil particles. The movement of ions within the pore water causes a transfer of moment to the pore water. Actually, why is it happening? We know that in a clay is negatively charged particle, and the thing is that you have adsorbed water on the clay surface, and also beyond that you have a pore water. Pore water also has certain chemistry, like it has its pH, it has its ionic concentration and all that. So, the this water, adsorbed water, is different from the pore water. So, this concept is very important. As students of soil mechanics, you must have studied all of this, and the corresponding direction rate of pore water movement are determined by the net transfer of the moment by both cations and anions within the pore water. So, how is the water movement taking place is essentially by the nature of momentum. The thing is that how many ions are getting altered or distributed. There are so many mechanisms that you have. It is based on the theory of diffuse double layer, in which the clay surface is treated as a layer, and next to that, because of the electroosmosis process, you have negatively charged particles, and then there is always a positive ions trying to go towards them, trying to balance out the valency. Okay. So, because of the nature of clay formation, which usually results in significantly negative charged clay particles, the predominant ions with the pore fluid are cationic, and water therefore moves from the anode to cathode. So, what happens is that near the cathode you have lot of water, like as I said, predominant ions in the pore water, say for example sodium ions or calcium ions, move with the pore fluid, or they go towards cation, cationic, and therefore they go towards cathode, right, cathode moving ions. Okay. So, all the predominant ions move towards the and from anode to cathode. Okay. This is very important concept, and so if you have a system of pumping water near the cathode, it is fine. Two fundamental factors that control the degree of water migration are the cation anion distribution, like say for example cation anion distribution, how many cations you have, how many anions you have, and what is the distribution and all that within the pore water, and the water cation distribution. So, for example, in the water, what is the cation exchange capacity of the soil is one important variable here. Then even the ionic concentration of the free water, there are all these chemical analysis needs to be done in a proper way, right. So, I will just show you a figure in which you have a typical ion distribution for a sodium saturated smectite or a bentonite immersed in a sodium chloride solution. The negative surface of the clay particle promotes a high cation anion ratio, and within the diffuse double layer. Actually, we know that next to the clay surface you have a diffuse double layer formation, and which is nothing but the adsorbed layer next to the clay particle, we say, and free water has a much lower cation anion ratio. So, the negatively charged surface of the clay particle has a high cation anion ratio quite naturally, because you have lot of negatively charged surfaces. So, cations tend to go there. So, the cations and anion ratio could be high within the diffuse double layer, whereas in the clay free water definitely the cation anion ratio is lower. This needs to be appreciated. A theory explaining the degree to which anions may migrate from the free water to the diffuse double layer and the associated effects on the electroosmosis was formulated by Donan 1924. In fact, you have anions in the free water, how many of them like will go to the diffuse double layer, and the associated effects are given in a particular book, particular reference, but it was quite useful in understanding the many of the, there could be some difficulties because it was formulated a little last century maybe, but the understanding that it gave was quite useful in understanding this phenomenon of stabilization of soils using this electrokinetic mechanisms, because it helps in controlling the chemical changes, because it has there are number of variables here. One is the pH of the water, then the adsorbed water content, and also the physical behavior of clay. So, this is what I just mentioned. These are all negatively charged particles. You have the clay particle, this is another clay particle, and you have sodium ions here which are there, this internal phase, external solution phase, this is another one in which you have this so much in excess. The thing is that these are all a balance here, but then these are all excess ions. Okay. So, this water cation ratio is something that is very important, and the purpose here is that we would like to remove water. We may call it electroosmotic water, because electroosmosis is a force that is applied to remove the water. So, we try to express in terms of the charge, unit charge W is proportional to water cation ratio, quite obviously, because higher is amount of water present, higher is amount of water cation ratio, higher is amount of water you can withdraw. If the water content is going to be less, you do not have much opportunity to remove water. So, the electroosmotic water flow per unit charge, we call it because it is more chemistry based terminology, which we should understand because the chemistry is very important in this context. So, the electroosmotic water flow per unit charge is proportional to the water cation ratio in the diffuse double layer. The relationship may be modified to take into account such effects as friction or drag between either the water and the solid or water and ion. So, there could be some drag effects because it is all number of ions and different types of ions being present, but still what happens is that, so you can see this equation where water or the electroosmotic water is proportional to the ratio of molar concentration of water divided by molar concentration of cations within the diffuse double layer. We know what is molarity. Molarity is nothing but one molecular weight dissolved in 1 liter of water, right, or the solute or whatever. So, we essentially need to understand those terminology, and as we can see that this amount of water that you can get out of this system is a function of the molar concentration of the water, and also inversely proportional to the molar concentration of cations within the diffuse double layer. Like say if you have more concentrations in the diffuse double layer, they hold the water, free water will not come. So, it is to that extent it has that meaning here, that so the high cation exchange capacity clays with low water contents, the W will be low, that is what I just mentioned. So, for example, if the clay surface has high negative charge, definitely the molar concentration of cations will be higher, because they go there, So, the water, so this is an important, so thus in the high cation exchange capacity place with low water content, W will be low. Okay. The low water content means the availability of water itself, okay, will be low, and as the water transferred per ion equivalent or quantity of electricity will be low. Like you can see that from such relationships it is possible to predict the behavior of clay in terms of the electroosmotic efficiency, like we try to call it in terms of the electroosmotic efficiency at different water contents. Like you can say that if it is in a dry state or a wet state or even close to optimum moist content, one can find out some of these properties. So, the amount of water that we can expect is a function of the water content, the cation exchange capacity and the cation anion ratio between the diffuse level layer and the free water system. There is another term that we should see, that the terms active and inactive are something that are related to the size of the diffuse double layer, and hence on the volume of the water present within the pore solution available for electroosmotic transport. What it means is that if the clay is very active, how do you define the activity of the clay? Activity is defined as the ratio of the plasticity index to the percentage of the clay size particles. So, Pi we have some number divided by the percentage of the clay particles is what we define as activity, and if the material is active, what does it mean? Active in the sense, actually this activity is defined in terms of the negatively charged surfaces, and definitely you can see that this activity and inactivity whatever has a significant influence. We will see in this particular figure that inactive, low exchange capacity and high water content. The water content, one can have a very high water content removal from that. Inactive, low water content, low exchange capacity and low water content, this is another one. And very active, like the say for example bentonite and all that, and high exchange capacity and high water content is one, and then definitely active, high exchange capacity, low water content. If water availability is there, definitely you will have a higher yield or the water content removal from the soil because of the electroosmotic forces, right. So, the electroosmotic forces are quite useful in removing the water. So, this also in fact one should know that it is a function of the molarity or the normality. See, normality of the external electrolyte is again another variable, and these two terms, normality and molarity and molality, they are all we studied in our basic sciences in our curriculum. And say for example, molarity is nothing but the as I just mentioned, you take a sodium chloride and it has a molecular weight of 40, and if it is dissolved in 1 liter of water or the solute or whatever you call it, we call it 1 molar. And normality comes in terms of the equivalent weights, it is much more standardized, and we talk in terms of the normality also, and higher is the normality, like say for example, it is 1 here, 0.1 here, 0.01, 0.0. So, you dilution, you add dilution factors are there, like instead of 1 liter you say only 100 ml. So, dilution is there, and so based on the dilution factors also it has a significant role. Okay. This is what we understand from the clay science. What are the other effects of electrical application? So, once we apply the electrical gradients, what happens is that the movement of water reduces both the water content and the pore water pressure. Okay. So, it increases the net effective stress. So, the moment there is a effective stress increase, there is an effective strength also, strength is increasing, right. Then you have electrolysis of the pore water at the electrodes. So, you have the electrolysis taking place, which causes hydrogens and hydroxyl ions to be released from the anode, and there is a sort of you have H plus and OH minus ions getting released, and you have this sort of chemical reactions taking place, right, because this is what happens. These ions are drawn towards the opposing electrodes. Therefore, there are differentials in the pH levels across the soil mass. Because of the changes in electrical gradients, there could be pH variations also. So, these pH variations in turn change the surface charge of the clay minerals, and thus the cation exchange capacity. So, what happens? Originally the cation exchange capacity was something very different. So, for example, we say that bentonite has so much cation exchange capacity, or this illite has so much CEC, we call it cation exchange capacity. So, all that gets altered, and also so because of these changes, when the migration of ions takes place from anode to cathode and cathode to anode, whether it is hydroxyl ions or hydrogen ions. So, there is a change in the soil structure itself. So, that leads to in fact somewhat stronger condition here. Okay. So, that is within the soil. So, what happens when you have electrodes? The reactions that occur between the electrodes and the pore water depend on the characteristics of the pore water and the material properties of the electrodes. So, suppose you are using mild steels, what happens is that definitely when you put water, corrosion takes place, right. So, this is what happens, like iron gets converted to ferric material, and so there is this sort of chemical reactions, oxidation at the anode takes place, reduction at the cathode takes place, you have a combined influence like this. So, again it gets to ferrous to ferric, it gets converted, and this sort of chemical reactions do take place, and which is something which even we are familiar with some sort of corrosion that could occur. So, mild steel electrodes were used in some studies, which is quite standard material. From the corrosion theory, we know that the oxidation occurs at the anode owing to the loss of electrons, while reduction occurs at the cathode. This is what is shown by these two chemical reactions, and you have a combined also. So, further oxidation takes place. Okay. So, having this knowledge, how do you go about design? It is actually we do not have much work that is done in India, but elsewhere in the rest of the world there is considerable knowledge, expertise, or at least a lot of practical studies have been done In fact, in 1963 itself, in 1960s, if you remember, Casagrande, who is known as one of the top top researchers or the engineers in geotechnical engineering, he contributed to this. He is the first man who demonstrated that the stability of the slope can be improved using electroosmosis. He did some experiments. So, what is required in this? Some of the issues we should discuss. Then correct electrode installation. Say we have a cathode, you have an anode, and it should have good electrical contact with the subsurface. There is a clay soil, and when you put this material like anode and cathode, they are small tubes. Okay, it can be just which you can put inside, or it can be bigger like 100 in the field. What I did in the lab was a small tubes, because it is comfortable, they are available, though I just put, because my clay the small plastic container was about 1.5 to 2 feet higher, and then I just put some tubes which were acting as anodes and cathodes. So, correct electrode installation requires or ensures good electrical contact with the subsurface. They should be properly contact there, while avoiding an electrical bridge through the surface of the topsoil. What happens? There should not be a short circuiting type of thing, where there is a that bridge formation should be avoided. Okay. Low electrical resistance can be maintained in the soil by ensuring high degree of saturation. Okay. Sometimes if you just add water and all that, degree of saturation is higher, and then maintain that systems. We have essentially we all would like to avoid the bridge formation, short circuiting. Subsurfaces such as slip surfaces and sands, gravel lenses may provide electrical bridges where injected stabilizers will preferentially migrate. Actually, what we do is that, say sometimes in say in the in situ soil, there could be some small slip surfaces, some gravel and all that. The possibility is that even through them the electrical bridges can form, which could be avoided. So, why? Because actually we inject in this whole technique some sort of stabilizers, and the possibility is that the stabilizers will get migrated into the system, that we would like to avoid. Okay. Then you have, how do you do this? Augering or augered holes may have to be sleeved to prevent infill. Okay. Side wall raveling or collapse, in which case selection of sleeve material requires careful consideration. Say for example, you are trying to make a hole. So, the hole should be able to work in a proper way, so that it should not collapse. So, the sleeve material selection is an important factor. Then the effect of any acid or base front propagation through the soil must be considered, particularly in relation to underground services. Actually, when you are trying to do in an excavate some area in an urban area or something, where you have a lot of underground structures like PVC pipes and many other chemical or even steel pipes or anything, service lines, one should be very careful that say for example, the some of the distribution of cations and anions should not lead to damaging the underground services. Okay, that is important point. If the treatment is being carried out on the existing structures, great care must be taken to control the depth of water table to avoid unwanted ground movement. Actually, that is another important point, as I just mentioned, that the water table control is very important. Like water table you can remove in one place, but at the same time where it is important, you should maintain the water table by again putting water back at least close to that foundation area, so that we do not want increase in effective stress and below the foundation. We only want water removal somewhere, not beneath the foundation also. So, one should be very careful in removing the water, particularly close to foundations. So, this is a typical example. Actually, these are number of lot of research has been done, and a number of the papers published on these lines. For example, Bailey and Atenscu in 1961. Okay. This is a paper on the application was mine tunnel strengthening. say you are trying to do tunneling, and then when you want to strengthen the tunnels, one should really use some sort of stabilizers also, proper stabilizers, so that all these things electrokinetic stabilization is successful. So, the soil type was fine silty sands, silicate, the stabilizer used was silicates and calcium chloride solutions, because to accelerate the process in that thing one should use this. The application, the comment, it was successful. And then there is another paper where in a Seattle Tacoma in US International Airport runway, the soil is clay and they have used some sort of stabilizer, dehydrogenated tallow dimethyl ammonium chloride, whatever. Okay. Then the application was successful. Then there is another paper where is a laboratory study, the soil type was illite and calcium chloride was used, calcium ion found to be optimum for illite stabilization. So, they were trying to look at calcium ion and does it help. There is another paper on Carroll, reservoir construction in Tunisia, very soft soil, ammonium chloride was used, it increases shear strength. Then there were some more papers on Carroll, again foundation for bridge abutment, soft to stiff clay, sodium silicate was used as a stabilizer. There was major implementation problems encountered, that is one thing. Then Yamaguchi and Matsuda in 1975, you have laboratory studies, liquefiable sand, people use the silicate solutions and bentonite and aluminum hydroxide. So, the application was successful. So, you have Bannon in 1976, it is highways upgrade Arizona US, low plasticity clay, potassium chloride. So, reductions in the degree of swell and swell pressure, that was there. Then there is another one 1977, foundation strengthening, it is a Loess deposit, sodium silicate was used as solution, it is a successful application. Anion, again it is a laboratory study, kaolinite was the clay soil type, aluminum and phosphate ions were used, large increase in shear strength for phosphoric acid than aluminum sulphate they observed. Shear strength values, so for example, they took two types of ions, aluminum and phosphate, and they find that you have an excellent benefit from the phosphoric ions, phosphate ions. And these are laboratory studies, kaolinite, aluminum and phosphate ions, it was successful laboratory investigations. So, you have number of studies that really were quite helpful in giving a confidence to the professions in use of this technique.